In the vast tapestry of the night sky, stars hang like ancient embers, their light a whisper from epochs long faded. These celestial fires scattered across the infinite canvas stand as silent sentinels to the unfolding drama of existence. Each one, a colossal furnace, transmutes the simplest elements into radiant energy, burning its core essence into beams that pierce the void, traveling for millennia to reach the eyes of distant observers. They are the architects of worlds, forging the heavy atoms that compose planets, oceans, and life itself, in a ceaseless cycle of creation born from their own fiery hearts. Yet, the story of stars is not solely one of unrelenting blaze and cataclysmic end. The human imagination often conjures visions of stellar demise in grand spectacles, supernovae erupting with the force of billions of suns, scattering debris across galaxies in a final, furious roar. But the cosmos harbors subtler narratives, paths less traveled where the end comes not with thunder, but with a profound stillness. Some stars, after exhausting their fuel, do not explode into oblivion. Instead, they retreat into a quiet metamorphosis, their once molten interiors solidifying in a transformation as elegant as it is enigmatic. This is the realm where fire yields to crystal, where the heart of a star crystallizes into something enduring, a testament to the universe's capacity for unexpected grace. Imagine, then, a scene unfolding in the frigid expanse of the Milky Way, far beyond the reach of human vessels. There, adrift in the interstellar silence, resides a remnant of what was once a vibrant sun. No longer does it pulse with the heat of fusion. Its glow has dimmed to a faint shimmer, a ghostly afterimage against the backdrop of eternal night. Deep within this cooled husk, the core has undergone an alchemical shift. Under pressures inconceivable to earthly minds, forces that compress matter, towed cities where atoms themselves strain against the crush, the carbon remnants of its former life have aligned into a lattice of unparalleled purity. This is no mere rock or mineral. It is a diamond vast and flawless, spanning diameters rivaling that of our own planet, not a gem to be mined or worn, but a cosmic jewel suspended in the abyss, reflecting the faint light of neighboring stars in its crystalline facets. It floats there, unchanging, a monument to this star's final act, enduring while galaxies whirl and empires of dust rise and fall around it. Humanity has long revered diamonds as emblems of the eternal. Forged in the depths of Earth under volcanic fury, they emerge as symbols of rarity and unbreakable bond, tokens of love sealed in proposals, heirlooms passed through generations, artifacts of permanence in a world of flux. Their clarity captivates, their hardness defies time, evoking a sense of immortality that resonates in myths and markets alike. Yet the universe crafts these wonders on a scale that dwarfs our terrestrial treasures. In the stellar forges, diamonds are not anomalies but inevitable outcomes for certain paths of evolution. A single such crystal core could encompass masses equivalent to that of our Sun, compressed into a sphere the size of Earth, its atoms locked in adamant structure that withstands the ravages of cosmic eons. This is nature's extravagance. What we prize as scarce and precious, the stars produce in abundance, hidden in the remnants of their faded glory, challenging our notions of value and wonder. But how does such a transformation occur? What arcane mechanisms of the physical world conspire to turn the inferno of a star into this solidified splendor? The journey begins in the star's youth, when it shines much like our own sun, fusing hydrogen into helium in its core through nuclear reactions that release tremendous energy. This process sustains the star for billions of years, a delicate balance where gravity pulls inward and the outward push of radiation holds collapse at bay. As the hydrogen depletes, the star evolves, swelling into a red giant, its outer layers expanding while the core contracts and heats, igniting heavier elements in successive shells. Helium fuses to carbon, carbon to oxygen, each stage a step toward exhaustion. For stars of moderate mass, those roughly 1 to 8 times that of our Sun, the endgame diverges from the explosive fate of their more massive kin. Lacking the heft to forge iron and trigger a supernova, they shed their outer envelopes in a gentle expulsion, forming luminous clouds known as planetary nebulae. What remains is a white dwarf, a dense Earth-sized core composed primarily of carbon and oxygen, supported not by fusion but by the quantum resistance of electrons, a phenomenon where particles refuse to occupy the same space, creating a pressure that defies further collapse. As this white dwarf cools over trillions of years, far longer than the current age of the universe, its interior temperature drops, and the ions within begin to arrange themselves into an ordered grid. At densities where a single teaspoon of material weighs as much as an elephant, the carbon atoms crystallize, forming a diamond lattice that propagates from the center outward. This solidification releases latent heat, subtly slowing the cooling process, much like the freezing of water liberates energy. Observations from space telescopes have revealed pulsations in these objects, vibrations that allow astronomers to probe their interiors, confirming the presence of such crystalline structures in select white dwarfs. One such example, located thousands of light years away, has been studied through its variable brightness, suggesting a core largely transformed into diamond, a finding echoed in theoretical models that predict this phase transition under extreme conditions. This revelation invites a deeper philosophical contemplation. The universe, often portrayed as a theater of destruction, where black holes devour, galaxies collide, and entropy marches toward disorder, reveals here a counterpoint of preservation and renewal. A star's death is not an erasure but a reconfiguration, its volatile energy giving way to a form of quiet immortality. The diamond core endures, potentially outlasting the stars that still burn, a silent archive of the universe's history etched in atomic bonds. It prompts reflection on transformation. Just as carbon born in stellar nurseries cycles through planets and life forms before returning to the void, so too does the cosmos recycle its essence in ways that blend destruction with creation. In this crystallized heart, one glimpses the universe's dual nature, fierce in its births, serene in its legacies, reminding us that permanence arises not despite change, but through it. What forces sculpt this metamorphosis? At the quantum level, the Pauli exclusion principle governs the electron degeneracy pressure that halts the white dwarf's collapse, a rule of nature where no two electrons can share identical states, creating an invisible scaffold against gravity's pull. As cooling proceeds, the Coulomb forces between ions overpower thermal chaos, leading to crystallization. Theoretical physics, drawing from condensed matter studies on Earth, extends these principles to stellar scales, predicting that in carbon-rich white dwarfs, the transition occurs at temperatures around millions of degrees Kelvin, far hotter than any terrestrial forge, yet yielding a structure akin to diamond's cubic symmetry. Speculatively, yet grounded in credible extensions of known physics, one might ponder the longevity of these diamond worlds. In the far future, as the universe expands and cools, these remnants could persist as the last luminous objects, their faint glow sustained by the slow release of crystallization heat. They become cosmic time capsules, encoding the chemical signatures of their progenitor stars, offering clues to the galaxy's evolutionary saga. If binary systems pair them with companions, gravitational interactions might one day shatter or reshape them, scattering diamond fragments across space. Though such events remain hypothetical, they underscore the dynamic interplay between stability and inevitable change. In evoking this mystery, the diamond star stands as a bridge between the infinitesimal and the infinite, a symbol of how the laws that govern subatomic particles manifest in galactic wonders. It challenges perceptions of endings, suggesting that death in the cosmos is but a prelude to new forms of existence. As humanity gazes upward, Drawn by the allure of these eternal jewels, one reflects on our own fleeting place amid such grandeur. A reminder that in the universe's vast narrative, transformation is the truest constant, turning fire into crystal, chaos into enduring beauty. In the vast cathedral of the cosmos, where stars burn as candles against the eternal night, most will not meet their end in fiery cataclysms. Instead, they follow a quieter path, one that leads to a state of serene endurance. These are the white dwarfs, stellar remnants, the embers left after a star has exhausted its nuclear fuel. No longer ablaze with the fury of fusion, they linger as compact cores, roughly the size of Earth yet harboring the mass of a sun. Their surfaces, once molten, cool over eons, their glow fading like the last breath of a dying flame. These relics, numbering in the billions across the Milky Way, are the inevitable destiny of stars like our own sun, humble in their final form, yet profound in their testimony to the universe's cycles of birth and decay. The quest to understand these stellar ghosts has long captivated astronomers, who peer into the heavens with instruments attuned to the faintest whispers of light. In the late 20th century, the search for such remnants became a meticulous endeavor, mapping the graveyard of stars to uncover their secrets. Observatories scanned the skies, cataloging objects that no longer burned but shimmered faintly, their surfaces radiating the residual heat of their former lives. Each white dwarf was a puzzle, its composition and structure a cipher to the processes that govern stellar evolution. Telescopes, both ground-based and orbiting, became the tools of cosmic archaeologists, sifting through the light of these ancient relics to piece together their stories. Among these distant embers, one star stood apart, its light carrying a mystery that would redefine perceptions of stellar endings. Located some 50 light-years from Earth, in the constellation Centaurus, this object was catalogued as BPM 37093. To the naked eye, it was invisible, a faint speck lost in the crowded firmament. But to the astronomers who studied it, it was a beacon of intrigue. Identified as a white dwarf, its unassuming appearance belied a hidden complexity. Its light, observed through precise measurements, flickered in a rhythmic dance, pulsations that hinted at a structure unlike any other. These vibrations, subtle as the ripples on a cosmic pond, were not mere quirks but signals, carrying secrets from the star's core to the surface, where instruments could capture them. In the early years of the new millennium, a team of astronomers, led by Travis Metcalf and colleagues at the Harvard-Smithsonian Center for Astrophysics, turned their attention to this enigmatic star. They employed a technique known as asteroseismology, a method akin to listening to the heartbeat of a star. Just as geologists study seismic waves to probe Earth's interior, these scientists analyzed the pulsations of BPM 37093 to map its unseen depths. The star's oscillations, variations in brightness caused by internal vibrations, acted as a cosmic sonogram, revealing the density, composition, and state of its core. Each pulse was a note in a symphony, played on the strings of gravity and pressure, resonating through layers of matter compressed to unimaginable density. What they uncovered was nothing short of extraordinary. The data suggested that the star's core, composed primarily of carbon and oxygen, had undergone a profound transformation. Under the crushing pressures within, where a single cubic centimeter of material could weigh as much as a mountain, the carbon atoms had aligned into an ordered lattice. This was no longer a fluid or gaseous core, but a crystalline structure, a diamond forged in the heart of a dying star. The implications were staggering. Here was a celestial body, once a blazing furnace, now solidified into a gem of cosmic proportions, its diameter rivaling that of Earth itself. The star, in its quiet senescence, had become a monument of permanence, whole crystalline relic floating in the interstellar void. This discovery was not merely a triumph of observation, but a testament to the universe's capacity for alchemy. The idea that a star could end its life not in destruction, but in crystallization, captivated the scientific community and beyond. The star was affectionately dubbed Lucy, a nod to the Beatles' song Lucy in the Sky with Diamonds, a name that carried both whimsy and reverence. It evoked images of a celestial jewel sparkling in the cosmic night, a symbol of beauty, born from the ashes of stellar fire. Yet beneath the poetic allure lay a rigorous truth, grounded in the physics of extreme conditions. The crystallization process, predicted by theoretical models, was driven by the same forces that govern matter on Earth, scaled to realms where gravity and quantum mechanics intertwine. To understand this transformation, one must journey back to the star's earlier life. Like our Sun, BPM 37093 once burned hydrogen in its core, sustaining itself for billions of years through nuclear fusion. As its fuel dwindled, it swelled into a red giant, its outer layers expanding while its core contracted, igniting heavier elements in a desperate bid to stave off collapse. For stars of its mass, roughly comparable to the Sun's, the journey ended not in a supernova's blaze, but in a gentler shedding of its outer envelope. What remained was a white dwarf, a dense core supported by electron degeneracy pressure, a quantum phenomenon where electrons, packed tightly, resist further compression. This pressure, arising from the Pauli exclusion principle, holds the star against gravity's relentless pull, creating a stable remnant that cools slowly over cosmic timescales. As the white dwarf cools, its internal temperature drops, and the ions within its core begin to settle. At densities where a sugar cube's worth of material could outweigh an ocean liner, the carbon ions, once jostled by thermal energy, find order. They align into a crystalline lattice, much like the diamond structure found in Earth's mantle, but on a scale unimaginable. This transition, occurring at temperatures still millions of degrees, releases latent heat, subtly delaying the star's cooling, a process akin to water freezing into ice, where energy is liberated as the structure solidifies. Asteroseismology confirmed this in BPM 37093, as its pulsations matched models of a crystallized core, with up to 90% of its mass locked in this diamond-like state. The discovery of Lucy was a milestone, but it also opened a window into broader questions. How common are such crystalline cores among white dwarfs? Theoretical studies suggest that many, perhaps most white dwarfs undergo this transformation as they age, their interiors solidifying over trillions of years. Observations of other pulsating white dwarfs, combined with data from space telescopes like the Hubble and Kepler, have supported this, revealing similar signatures in their vibrations. The Milky Way, it seems, is strewn with these cosmic gems, each a testament to the universe's ability to craft order from chaos, permanence from ephemerality. Yet the story of Lucy is not merely one of scientific triumph, it is a meditation on the nature of endings. The universe, often depicted as a realm of entropy and dissolution, reveals here a counterpoint of preservation. A star's death is not an obliteration, but a metamorphosis, its core transformed into a structure that could endure beyond the lifetimes of galaxies. These diamond cores floating silently in the void are archives of cosmic history, their atomic bonds encoding the chemical legacy of their progenitor stars. They challenge the notion that all things must fade, suggesting instead that transformation is the universe's truest art. Speculatively, one might imagine the fate of these crystalline relics in the far future. As the universe expands, cooling toward a state of diffuse darkness, white dwarfs like Lucy may become the last luminous objects, their faint glow sustained by the slow release of crystallization energy. They could serve as beacons for hypothetical observers in a universe grown dim, their diamond hearts preserving the memory of a once vibrant cosmos. If paired with a companion star, gravitational interactions might one day disrupt their serenity, perhaps fragmenting them into shards that drift through space, an outcome plausible yet distant, grounded in the dynamics of binary systems observed today. The discovery of BPM 37093 and its christening as Lucy marks a moment when humanity glimpsed the universe's capacity for wonder. It bridges the mundane and the cosmic, linking the diamonds we cherish on Earth to the stellar forges that craft them in abundance. It invites reflection on our place in this grand narrative, where the laws of physics weave stories of fire and crystal, chaos and order. As astronomers continue to probe the skies, each new finding adds depth to this mystery, reminding us that the universe, in its silent transformations, speaks a language of eternal renewal, where even in death, a star may shine as a diamond in the sky. In the shadowed depths of Earth, where molten rock churns beneath continents, diamonds are born. Forged under pressures that crush carbon into crystalline perfection, these gems emerge as emblems of rarity, their clarity a testament to the planet's hidden violence. To humanity, they are treasures, symbols of love, wealth, and endurance, mined from depths where heat and force conspire to sculpt the extraordinary from the mundane. Each diamond, no larger than a pebble or a fist, represents a triumph over chaos, a fragment of eternity wrested from the Earth's fiery crucible. Yet the cosmos, in its boundless extravagance, tells a different story. Far beyond the reach of human hands, in the cold silence of the interstellar void, entire stars transform into diamonds, vast gleaming cores that dwarf planets, their crystalline lattices spanning thousands of kilometers. This revelation, unveiled in the heart of a white dwarf named Lucy, shook the foundations of scientific understanding, challenging not only physics, but humanity's very sense of value and wonder. The discovery of Lucy, a white dwarf 50 light-years away in the constellation Centaurus, was no mere footnote in astronomical records. It was a seismic shift, a moment when the universe revealed a truth that seemed to defy the boundaries of possibility. On Earth, diamonds form in localized pockets where pressures reach a few gigapascals, immense yet confined to narrow veins beneath the crust. To imagine a diamond structure extending across an entire stellar core, encompassing a volume comparable to Earth itself, was to confront a scale of creation that bordered on the surreal. This was not a gem one could hold or cut, but a celestial monument forged under pressures billions of times greater than those beneath Earth's surface. The carbon atoms within, once part of a star's fiery heart, had aligned into a lattice of unparalleled purity, a cosmic crystal suspended in the abyss, its facets reflecting the faint light of distant galaxies. The possibility of such a transformation had been whispered in theoretical circles for decades. As early as the 1960s, physicists speculated that white dwarfs, the dense remnants of stars like our Sun, might undergo a peculiar evolution as they cooled. Unlike their progenitor stars, which burn through nuclear fusion, white dwarfs are sustained by a stranger force, electron degeneracy pressure. This quantum phenomenon arises from the Pauli exclusion principle, a rule dictating that no two electrons can occupy the same quantum state. In a white dwarf, where matter is compressed until a teaspoon of material weighs as much as an elephant, electrons are packed so tightly that they resist further collapse, creating an invisible scaffold that holds the star against gravity's relentless pull. This balance allows white dwarfs to persist, cooling slowly over trillions of years, their surfaces dimming as their internal heat dissipates into the void. Within this dense core, primarily composed of carbon and oxygen, a further transformation was hypothesized. As the white dwarf cools, its interior temperature drops below a critical threshold, and the chaotic motion of ions gives way to order. The carbon atoms, under pressures where each cubic centimeter bears the weight of a mountain, begin to align into a crystalline lattice, much like the diamond structure found on Earth. This process, driven by the Coulomb forces between positively charged ions, releases latent heat, subtly slowing the star's cooling, a phenomenon akin to the freezing of water, where energy is liberated as liquid becomes solid. Theoretical models predicted this crystallization, but proof remained elusive, a tantalizing possibility locked within the unseen depths of stellar remnants. The discovery of Lucy, or BPM 37093, changed that. Through the lens of asteroseismology, the study of stellar pulsations, astronomers glimpsed the star's interior. Its rhythmic variations in brightness, caused by internal vibrations, revealed a core that had largely solidified into a diamond-like structure. This was not mere speculation, but a conclusion drawn from precise measurements, supported by data from observatories and theoretical models refined over years. The star's pulsations matched predictions for a crystallized core, where up to 90% of its mass had transitioned into a lattice, its carbon atoms locked in a configuration that mirrored the gems humanity so revered. The announcement, led by researchers like Travis Metcalfe in the early 2000s, sent ripples through the scientific community, confirming a hypothesis that had lingered in the realm of theory for decades. This revelation was as unsettling as it was awe-inspiring. On Earth, diamonds are prized for their scarcity, their formation a rare alchemy of geology. In the cosmos, however, the universe crafts them with a casual abundance, sculpting entire stellar cores into crystalline forms. The paradox was stark. What humanity holds as precious, the universe produces in quantities that defy comprehension. A single white dwarf like Lucy could contain more diamond than all the gems ever mined on Earth, its mass equivalent to that of the Sun compressed into a sphere the size of our planet. This cosmic extravagance challenged human notions of value, suggesting that what we treasure as rare might be, in the grand tapestry of the universe, as commonplace as stardust. The implications extended beyond mere abundance. The discovery of Lucy raised a disquieting question. If the universe could so effortlessly create diamonds, what else that humanity holds dear might be mere cosmic debris? Gold, revered through millennia, is forged in the hearts of dying stars, scattered across galaxies in supernova explosions. The elements that form life itself, carbon, oxygen, nitrogen, are the byproducts of stellar furnaces, cycled through the cosmos in endless renewal. The realization that diamonds, symbols of eternity, are not unique to Earth but are woven into the very fabric of the universe, forces a re-evaluation of significance. Are these treasures truly rare, or are they simply fragments of a larger narrative, where the universe's alchemy renders the extraordinary ordinary? The physics of Lucy's transformation, though grounded in rigorous science, carried an air of the miraculous. Electron degeneracy pressure, the force that sustains white dwarfs, is a quantum marvel, a reminder that the universe operates on principles that transcend human intuition. As the star cools, the crystallization process begins at its center, where pressures are greatest, and propagates outward. This transition, occurring at temperatures still millions of degrees, mirrors the formation of diamonds on Earth, but on a scale that humbles terrestrial geology. Studies from institutions like NASA and theoretical work published in scientific archives have refined our understanding, showing that many white dwarfs likely undergo this process, their cores solidifying over cosmic timescales. Observations of other pulsating white dwarfs, using telescopes like Kepler and Hubble, have bolstered this, revealing similar signatures of crystallization in their vibrations. Speculatively, yet within the bounds of credible physics, one might ponder the future of these diamond stars. In the distant epochs of the universe, as galaxies dim and new star formation wanes, white dwarfs may become the last bastions of light, their crystalline cores enduring as silent witnesses to a cooling cosmos. Their faint glow, sustained by the slow release of crystallization heat, could outlast the lifetimes of galaxies, making them cosmic time capsules, preserving the chemical signatures of their progenitor stars. In binary systems, gravitational interactions might one day disrupt these relics, perhaps fragmenting their crystalline cores into shards that drift through space, an outcome plausible given the dynamics observed in close stellar pairs. The discovery of Lucy's diamond heart was a scientific shock, not because it defied the laws of physics, but because it revealed the universe's capacity to mirror Earth's wonders on an unimaginable scale. It forced a confrontation with the limits of human perspective, where the precious becomes commonplace and the extraordinary is woven into the fabric of existence. It is a reminder that the universe is not merely a realm of fire and destruction, but a crucible of transformation, where chaos gives way to order and death to enduring beauty. As astronomers continue to probe the skies, each new finding deepens this mystery, suggesting that the cosmos, in its silent alchemy, crafts monuments that outlast time itself, diamonds not just in the sky, but as the very hearts of stars, eternal in their crystalline repose. The discovery of Lucy, the diamond-hearted white dwarf shimmering 50 light-years away in Centaurus, was not an isolated revelation, but a beacon that illuminated a broader cosmic truth. Its crystalline core, forged from the ashes of a once blazing star, hinted at a process not unique but woven into the very fabric of stellar evolution. Astronomers, stirred by this celestial alchemy, turned their gaze to the heavens with renewed purpose, seeking to unravel whether such transformations were rare or commonplace among the galaxy's countless stellar remnants. The night sky, a tapestry of ancient fires, became a canvas for investigation, each white dwarf a potential archive of the universe's silent metamorphoses. What began as a singular marvel soon unfolded into a deeper exploration, one that would redefine the understanding of stars and their legacies, revealing a cosmos where diamonds are not anomalies, but the enduring echoes of stellar death. To probe these stellar ghosts, astronomers relied on a method as poetic as it was precise: asterosismology, the art of listening to the vibrations of stars. Like heartbeats pulsing through the void, these oscillations, subtle variations in a star's brightness, carry secrets from their cores to their surfaces. Each pulse is a resonance, a wave of pressure or gravity rippling through dense matter, shaped by the star's internal structure. By analyzing these rhythms, scientists could peer into realms no telescope could directly behold, mapping the unseen interiors of white dwarfs. Observatories across the globe, from mountaintop telescopes to orbiting instruments, captured these stellar symphonies, their data a chorus of frequencies that whispered of crystalline lattices forming in the hearts of cooling stars. The investigation expanded, driven by a hunger to know whether Lucy's diamond core was an outlier or a harbinger. Surveys of the night sky, conducted with meticulous precision, catalogued thousands of white dwarfs, each a relic of a star that had exhausted its nuclear fire. Instruments like those used in the Sloan Digital Sky Survey, a monumental effort to map the cosmos, collected spectra and light curves from these faint embers, revealing their temperatures, compositions, and pulsations. Later, the Gaia mission, with its unparalleled ability to measure the positions and motions of stars, added depth to this portrait, identifying white dwarfs across the Milky Way with exquisite accuracy. Among these, a pattern emerged. Many exhibited pulsations and cooling behaviors suggestive of crystallization, their interiors transitioning from fluid chaos to ordered solidity. Astroseismology confirmed what theory had long proposed. The crystallization of white dwarf cores was not a singular event, but a common destiny for stars of modest mass. As these remnants cool over billions of years, their internal temperatures drop, and the carbon and oxygen ions within, compressed to densities where a sugar cube could outweigh a mountain, begin to align into a lattice. This process, driven by the electrostatic forces between ions, mirrors the formation of diamonds in Earth's mantle, but unfolds on a scale that defies terrestrial imagination. The lattice forms first at the core's center, where pressures are greatest, and propagates outward, transforming the star into a crystalline sphere. Observations of pulsating white dwarfs, their vibrations analyzed with mathematical precision, revealed signatures of this transition, shifts in frequency that matched models of solidified cores. Data from telescopes like Hubble and Kepler bolstered these findings, showing that a significant fraction of white dwarfs, perhaps most, undergo this metamorphosis as they age. This discovery reshaped the science of cosmic clocks, a field where white dwarfs serve as chronometers for the galaxy's history. By measuring a white dwarf's surface temperature and luminosity, astronomers can estimate its age. As these stars cool predictably over time, their glow dimming as residual heat escapes into the void. This cooling rate, governed by the physics of radiation and conduction, allows scientists to date the stellar populations of galaxies, tracing the epochs when stars were born. Yet, the revelation of crystallization introduced a complication, a subtle twist in the cosmic narrative. As a white dwarf's core solidifies, the process releases latent heat, energy liberated as ions lock into their lattice, much like water releasing heat as it freezes into ice. This heat slows the cooling process, making the star appear younger than its true age, as if time itself hesitates in the presence of such enduring beauty. The implications rippled through galactic studies. Models that once assumed steady cooling had to be recalibrated, accounting for the energy released by crystallization. Surveys, including those from Gaia, revealed cooling anomalies in numerous white dwarfs, delays in their dimming that aligned with the onset of crystallization. These findings suggested that many of the Milky Way's white dwarfs, perhaps billions, harbor crystalline cores, their interiors transformed into diamonds that could outlast the galaxies themselves. This was not merely a matter of physics, but a philosophical shift, a recognition that the universe crafts permanence in the wake of stellar death, turning chaos into structures that endure through cosmic eons. Amid this deeper investigation, a profound realization emerged. Our own sun, the life-giving heart of our solar system, is destined for a similar fate. In approximately 5 billion years, its hydrogen reserves will dwindle, and it will swell into a red giant, its outer layers engulfing the inner planets in a fiery embrace. Mercury and Venus will vanish, consumed by the sun's expansion, while Earth may teeter on the edge of survival, scorched but intact. Eventually, the sun will shed its outer envelope, casting a luminous cloud, a planetary nebula, into the void. What remains will be a white dwarf, a dense core no larger than Earth, yet harboring nearly all the sun's mass. Supported by electron degeneracy pressure, this remnant will cool slowly, its surface fading from searing white to a dull ember over billions of years. In the far future, as the sun's white dwarf cools to temperatures where its carbon-rich core can no longer resist the pull of order, crystallization will begin. Over trillions of years, timescales that dwarf the current age of the universe, the sun's heart will solidify, its carbon atoms aligning into a diamond lattice. This cosmic jewel, invisible to any surviving observers, will drift through the galaxy, a silent monument to the star that once nurtured life. Its crystalline core, potentially spanning thousands of kilometers, will endure as a testament to the universe's capacity for transformation. A diamond born not from destruction, but from the quiet reordering of matter. This vision of the sun's fate invites reflection on the transient nature of existence. The star that has defined Earth's history Warming oceans and sparking life will one day become a relic, its legacy preserved in a form as enduring as it is alien. The process, grounded in the same physics that sculpted Lucy, underscores a universal truth. Endings are not erasures but transformations. The Sun's diamond core, like those of countless white dwarfs, will carry the chemical memory of its fiery youth, a record of fusion that forged the elements of planets and life. It is a reminder that the universe, in its relentless cycles, weaves continuity from change, crafting monuments that outlast the ephemera of worlds. Speculatively, yet within the bounds of credible science, one might imagine the far future of these crystalline relics. As the universe expands, its stars fading and its galaxies drifting apart, white dwarfs may become the last luminous objects, their faint glow sustained by the slow release of crystallization heat. These diamond cores could serve as cosmic archives, preserving the signatures of their progenitor stars for hypothetical observers in a darkened cosmos. In binary systems, gravitational interactions might disrupt their serenity, perhaps fragmenting their cores into shards that drift through space, an outcome plausible, given the dynamics observed in stellar pairs. Such fragments, if they exist, would be the ultimate relics, diamonds born of stars scattered across the void. The deeper investigation into white dwarfs, sparked by Lucy's discovery, revealed a universe where the extraordinary is routine, where diamonds are not rare gems, but the natural endpoint of stellar evolution. It challenges human perceptions of permanence and value, suggesting that what we cherish as unique is but a reflection of cosmic processes. As astronomers continue to map the skies, each pulsating white dwarf adds to this narrative, a story of fire giving way to crystal, chaos to order. In this silent alchemy, the universe speaks of endurance, crafting jewels that shine not with light but with the quiet beauty of eternal transformation, a legacy that lingers long after the stars have faded. Chapter 4. Escalation mystery deepens as the veil lifted on the crystalline heart of Lucy, a white dwarf 50 light-years distant in the constellation Centaurus. The cosmos whispered a truth far grander than a single stellar relic. What began as an isolated wonder, a star transformed into a diamond, unfolded into a revelation that echoed across the galaxy. Crystallization, once a theoretical curiosity confined to models and equations, emerged as a universal destiny for white dwarfs, the quiet endpoints of stars like our Sun. The Milky Way, that swirling river of light spanning 100,000 light-years, harbors billions of these remnants, each cooling in the interstellar silence. Many, perhaps most, conceal cores of diamond, invisible to the naked eye yet enduring beyond the lifetimes of worlds. These are not fleeting sparks, but eternal monuments, floating in the void, their atomic lattices a testament to the universe's penchant for crafting order from the remnants of fire. The night sky, long seen as a canvas of burning furnaces, now reveals itself as a graveyard of jewels, where the dead outshine the living in their silent permanence. The scale of this transformation defies the boundaries of human comprehension, a cosmic extravagance that renders earthly treasures insignificant. Consider Lucy alone, a white dwarf with a radius of approximately 4,000 kilometers, roughly 2/3 the size of Earth. Yet within this compact sphere lies a core composed primarily of carbon and oxygen, compressed to densities where a mere handful of material could outweigh a mountain range. Theoretical calculations, grounded in observations from space telescopes and asteroseismology, estimate that this crystalline structure equates to 10 billion trillion carats, a number so vast it stretches the imagination, a 1 followed by 34 zeros. This is no polished gem fit for a ring or crown, but a continent-sized lattice where carbon atoms align in a diamond configuration interspersed with oxygen, forming a structure of unparalleled purity and strength. Forged under pressures billions of times greater than those in Earth's deepest mines, this cosmic diamond floats adrift, its facets unseen, reflecting only the faint glow of neighboring stars. It is a relic of stellar evolution, a star's final act of defiance against entropy, solidifying its essence into a form that could persist for eons longer than the universe's current age. This escalation of wonder transforms the narrative of stars from one of mere combustion to profound metamorphosis. Stars, those colossal furnaces that forge the elements of existence, do not simply extinguish. They evolve into symbols of permanence, their volatile hearts yielding to crystalline repose. In their youth, they blaze with the fury of nuclear fusion, transmuting hydrogen into helium and heavier elements in a dance of gravity and radiation. As fuel wanes, they swell and shed, leaving behind white dwarfs sustained by quantum forces rather than fire. Electron degeneracy pressure, a quantum mechanical bulwark where electrons resist compression, holds these remnants aloft against gravity's inexorable pull. Over billions of years, as heat dissipates, the interior cools, and ions, once chaotic in their thermal motion, settle into an ordered grid. This crystallization, observed in Lucy and confirmed in numerous others through pulsating vibrations, marks a phase transition where matter achieves a new equilibrium, a lattice that mirrors the diamond's cubic symmetry but on a stellar canvas. The mystery deepens with the subtle mechanics of this transformation, a process that releases latent heat and alters the very rhythm of cosmic time. As the white dwarf's core solidifies, energy bound in the ionic bonds is liberated, much like the heat released when water freezes into ice. This infusion of warmth slows the star's cooling, extending its luminous phase and delaying the descent into darkness. Theoretical models, refined through data from surveys like those conducted by space agencies and ground-based observatories, show that this heat release can postpone cooling by billions of years. What was once a straightforward cooling curve, a predictable dimming used to gauge the age of stellar populations, now curves with an unexpected grace, influenced by the phase change within. Astronomers, who rely on white dwarfs as cosmic chronometers to date the galaxy's disk and halo, must recalibrate their timelines. The oldest white dwarfs, once thought to mark the universe's antiquity with their faint glow, may appear younger due to this lingering warmth, pushing back estimates of the Milky Way's formation and evolution. These diamond stars, far from being mere curiosities, emerge as architects of cosmic chronologies, rewriting the history etched in the stars. The cooling rates of white dwarfs serve as yardsticks for the age of star clusters and galactic structures, their luminosity functions mapping the epochs of star birth and death. With crystallization's influence, these models gain complexity. The release of latent heat creates a plateau in the cooling sequence, a hesitation where time seems to stretch. Studies from astronomical archives and peer-reviewed analyses indicate that this effect is pronounced in carbon-oxygen white dwarfs, the most common type, altering age estimates by up to 1 billion years in some populations. This recalibration ripples outward, affecting understandings of galactic formation, the timing of chemical enrichment, and the overall narrative of cosmic expansion. Diamond cores, invisible and enduring, thus become silent arbiters of time, their internal alchemy forcing a re-evaluation of the universe's calendar, where permanence begets delay and order tempers the march toward entropy. The haunting implication lingers in the quiet of the night sky, a subtle shift in perception that transforms the familiar into the profound. When eyes turn upward to the vault of heaven, dotted with points of light, some of those faint gleams are not the vibrant fires of living stars, but the subdued radiance of crystallized relics. white dwarfs, numbering in the hundreds of billions, within the Milky Way alone, contribute to the galaxy's diffuse glow. Their light a remnant heat rather than fusion's blaze. Among them, those with diamond hearts shine with a borrowed eternity, their surfaces still warm from the latent energy of solidification. This realization evokes a sense of melancholy wonder. The sky is a mosaic of life and legacy where the dead persist alongside the living. Their crystalline forms a bridge between the ephemeral and the eternal. It prompts reflection on the nature of visibility. What we see is but a fraction of what endures, the universe's true treasures hidden in the dim and distant. To grasp the universality of this fate, one must delve into the physics that governs it, a symphony of forces playing out in the stellar interior. White dwarfs form from stars of low to intermediate mass, those up to 8 times the Sun's heft, which expel their outer layers in planetary nebulae, leaving cores of degenerate matter. The Pauli exclusion principle underpins their stability, dictating that electrons cannot occupy identical states, thus generating pressure independent of temperature. As cooling proceeds, the core's ions, stripped of electrons, interact via Coulomb forces, their repulsion balanced against the crush of density. At temperatures around a few million degrees, still scorching by earthly standards but cool for stellar remnants, the thermal energy yields and crystallization ensues. This phase transition, predicted in theoretical papers dating back decades and confirmed through astrosismological data, propagates from center to periphery, solidifying the carbon-oxygen mixture into a lattice where carbon dominates the diamond-like structure. The escalation extends to the galaxy's hidden population, where surveys reveal a profusion of these jewels. Space missions, capturing the light curves of thousands of white dwarfs, show pulsations consistent with partial or full crystallization in a significant fraction. The Milky Way's disk, thick with stars born in recent epochs, hosts younger white dwarfs on the cusp of this change, while the halo's ancient remnants have long since solidified. This distribution maps the galaxy's history, with diamond stars serving as milestones. Speculatively, in the far future, as proton decay and black hole evaporation claim the last vestiges of matter, these crystalline cores may endure as the universe's final artifacts, their atomic bonds resisting the dissolution of time itself. Credible extension of current physics, where stability arises from quantum rules unyielding to entropy's advance. Yet the mystery's depth lies in its philosophical undercurrents, a meditation on transformation and legacy. Stars, symbols of transience in their blazing arcs, reveal through crystallization a capacity for rebirth in stillness. The universe, often cast as a realm of inevitable decay, counters with acts of preservation, turning stellar corpses into diamonds that outlast civilizations and epochs. This duality, fire yielding to crystal, chaos to lattice, mirrors broader cosmic themes where destruction forges creation and endings seed new forms. The latent heat's delay, a subtle reprieve in cooling, evokes the universe's reluctance to fade, a lingering warmth that extends narratives beyond expected bounds. In recalibrating chronologies, diamond stars compel humanity to reconsider time's flow, suggesting that the cosmos measures its age not in linear decline, but in layered transformations, each phase a chapter in an eternal story. In the vast silent expanse of the cosmos, where stars once blazed with the fury of creation now linger as fading embers, a profound transformation unfolds. Deep within the remnants of these ancient suns, known as white dwarfs. A quiet alchemy takes hold. As the relentless march of time strips away their residual heat, the dense plasma at their cores begins to surrender to order. Ions, once chaotic in their thermal dance, align into a crystalline lattice, a structure of exquisite precision born from the extremes of pressure and cooling. This process, commencing at the very heart of the star and radiating outward like the slow bloom of frost on a winter's pane, marks the passage from fluid turmoil to rigid eternity. Imagine a sphere the size of Earth, yet harboring the mass of the Sun, its interior compressed under forces that defy earthly comprehension, densities where a single spoonful weighs as much as a mountain range. Here, in this crucible of the universe, the physics of crystallization reveals itself not as a mere phase change, but as a cosmic elegy, a testament to the inexorable cooling of stellar souls. The journey begins in the aftermath of a star's demise. When a sun-like star exhausts its nuclear fuel, it sheds its outer layers in a gentle expulsion, leaving behind a core of degenerate matter. This white dwarf, glowing with the stored heat of its progenitor's life, embarks on a billion-year descent into obscurity. As temperatures plummet from millions of degrees to mere thousands, the ions, predominantly carbon and oxygen, the forged remnants of helium fusion, feel the grip of quantum forces tightening. Under pressures equivalent to millions of Earth's atmospheres, these particles can no longer roam freely. The Coulomb interactions, those electric repulsions that once kept them apart, now compel them to settle into a lattice, minimizing energy in a bid for stability. This crystallization is no abrupt event. It propagates gradually, layer by layer, from the densest core outward, much like the formation of ice in a freezing lake, where the depths solidify first, while the surface remains liquid. Scientific models drawn from molecular dynamic simulations paint a phase diagram of this transition, a boundary where liquid plasma yields to solid crystal, influenced by the ratio of carbon to oxygen. In cores rich in carbon, the lattice assumes a form akin to diamond, tetrahedral bonds echoing the gemstones buried in planetary mantles. Oxygen, heavier and more abundant in some dwarfs, introduces variations, sometimes leading to phase separation, where oxygen-rich crystals sink, displacing carbon upward in convective currents. This subtle dance alters the star's cooling curve, releasing latent heat that briefly halts the dimming, a final sigh before the long night. Consider the role of carbon and oxygen in this stellar metamorphosis. These elements, born in the stellar furnace through the triple alpha process and subsequent reactions, dominate the composition of most white dwarfs. Carbon, with its 4 valence electrons, favors strong covalent-like bonds under compression, while oxygen, with 6, adds complexity to the mixture. At densities where atoms are stripped to bare nuclei, surrounded by a sea of degenerate electrons, the behavior mimics that of a classical plasma, yet quantum effects prevail. Temperatures in the crystallizing core hover around millions of degrees, hotter than the sun's heart, yet the immense pressure, on the order of 1022 Pascal, enforces order. Observations from space telescopes, analyzing the spectra of these dwarfs, confirm the presence of such interiors. Pulsations in their light reveal seismic waves rippling through crystalline layers, much like earthquakes betraying Earth's solid core. In one such star, a white dwarf some 104 light-years distant, astronomers have detected the onset of this crystallization, its core transitioning to a diamond-like state, a celestial jewel in the making. The process is not uniform. In mixtures where carbon and oxygen coexist unequally, eutectic points emerge, akin to the freezing of alloys on Earth, where one element solidifies first, enriching the remaining liquid. This segregation can drive convection, stirring the interior and prolonging the dwarf's luminosity, a mechanism that reshapes our understanding of stellar ages. Indeed, the cooling histories of these objects serve as chronometers for the galaxy, their crystalline phases marking epochs in cosmic time. Yet, as we delve deeper into this crystalline realm, speculation beckons. extending the narrative beyond isolated stars to the grander tapestry of planetary formation. What if these diamond hearts are not mere endpoints, but harbingers of new worlds? Enter the enigmatic diamond planets, worlds forged in the fires of pulsar systems, where the extremes of stellar evolution yield crystalline surfaces. Pulsars, the spinning neutron stars born from supernova explosions, often strip material from companion stars, leaving behind dense remnants. One such world orbits the millisecond pulsar PSR J1719-1438, a mere 4,000 light-years away. This planet, no larger than Jupiter yet 5 times its mass, circles its host in a blistering 2-hour orbit, so close that tidal forces have compressed its carbon core into a crystalline form, essentially a diamond sphere. Formed perhaps from the eviscerated white dwarf companion of the pulsar, its surface may gleam with facets of compressed carbon, enduring radiation that would incinerate lesser worlds. Such planets challenge our notions of habitability. Their atmospheres, if any, would be tenuous veils against the pulsar's beam, yet their existence hints at resilience in the universe's harshest corners. Other candidates, like those around pulsar PSR B1257+12, suggest that diamond worlds could be common in these systems, survivors of cataclysmic births where supernova debris coalesces under neutron star gravity. This leads to a tantalizing hypothesis. Could crystallized white dwarfs serve as seeds for carbon-rich planetary systems? In the Milky Way, white dwarfs have been observed as primary distributors of carbon, their atmospheres polluted by the debris of shattered asteroids and planets. Spectral lines reveal accreted material rich in carbon, oxygen, and even water-bearing minerals, implying that these stars once hosted systems akin to our own. As a white dwarf cools and crystallizes, gravitational perturbations from distant companions might destabilize orbiting bodies, sending rocky fragments spiraling inward to vaporize on its surface. Yet in a broader sense, the carbon ejected during the star's earlier planetary nebula phase could seed interstellar clouds, fostering new generations of stars and planets enriched in this life-essential element. Observations of open clusters, ancient stellar groupings, show white dwarfs with unexpectedly high carbon abundances, suggesting they contribute to galactic carbon budgets. Imagine a scenario where a crystallizing white dwarf, its core a diamond archive of fusion history, disrupts a nascent planetary disk, dispersing carbon-laden dust that coagulates into exoplanets. This process might explain the prevalence of carbon-rich worlds, like those hypothesized around red dwarfs or even our own solar system's carbonaceous asteroids. The rapid formation of exoplanetesimals around white dwarfs, evidenced by polluted atmospheres, indicates that planetary building blocks assemble swiftly, perhaps within millions of years, concurrent with the star's cooling. Thus, these diamond stars could be cosmic forges, their crystalline legacies propagating through generations of systems, embedding the universe with the stuff of potential life. Venturing further into the speculative, one ponders the allure such objects might hold for advanced civilizations. In a galaxy teeming with possibilities, a crystallized white dwarf, its core a vast diamond enduring for eons, presents an artifact of unparalleled value. Would sentient beings evolved under distant suns seek to mine these stellar gems? The engineering feats required stagger the imagination. Harvesting from a body with surface gravity thousands of times Earth's, where escape velocities approach a fraction of light speed. Yet for a species mastering fusion or antimatter drives, the diamond core could yield inexhaustible resources, carbon lattices for megastructures, or even quantum computing substrates resilient to cosmic rays. Alternatively, perhaps these diamonds would be venerated, not exploited, sacred monuments to stellar mortality, orbited by temples or observatories, where philosophers contemplate the universe's transience. In pulsar systems, a diamond planet might serve as a fortified outpost, its crystalline shell shielding habitats from radiation, allowing civilizations to harness the pulsar's energy beam like a perpetual lighthouse. Speculations abound of Dyson spheres encircling white dwarfs, vast shells capturing their fading glow for eons-long sustenance. White dwarfs, stable and long-lived, could host such constructs more feasibly than volatile main-sequence stars, their compact size enabling efficient energy collection. If intelligent life persists through stellar epochs, these crystallized remnants might become beacons, studied as repositories of ancient data, magnetic fields encoding the progenitor star's history, or seismic pulsations narrating galactic tales. Their mystery deepens. Could magnetic anomalies in some white dwarfs hint at artificial interference, convective currents manipulated by alien probes to extract heat or information? Broadening the lens, these diamond stars invite profound philosophical reflection. Are they the jewels of the universe? Eternal monuments erected by the inexorable laws of physics from the ashes of dead stars? Each crystallized white dwarf stands as a record of cosmic history, its lattice preserving the isotopic signatures of nucleosynthesis, the scars of supernova companions, the echoes of planetary births and deaths. In their slow fade to black dwarfs, hypothetical endpoints where even crystallization yields to absolute cold, they embody the universe's entropy, a reminder that all light eventually succumbs to darkness. Yet in this finality lies beauty. The transformation from chaotic fusion to ordered crystal mirrors the cosmos's quest for equilibrium, a poetic symmetry in the grand design. They challenge your anthropocentric views, suggesting that life's precursors, carbon's versatile bonds, emerge not from benevolence but from stellar demise. As sentinels of time, white dwarfs chronicle the galaxy's star formation, their luminosity functions mapping epochs of birth and quiescence. In contemplating them, one senses the universe's indifference, yet also its elegance. A diamond forged in stellar depths, adrift in the void, whispering secrets to those who listen across the light years. What stories do they hold of the stars that birthed them, of the worlds they might seed? In their crystalline silence, they pose eternal questions about origins, endurance, and the fragile spark of existence amid the infinite night. This chapter, woven from the threads of observation and conjecture, illuminates the crystalline destiny of white dwarfs, not as an end, but as a bridge to new mysteries. The physics of their transformation, the speculative worlds they inspire, and the philosophical depths they plumb converge in a narrative of cosmic continuity. As the universe expands into chill obscurity, these diamond hearts endure, silent guardians of the stellar legacy, inviting us to gaze deeper into the abyss where science and wonder entwine. In the shadowed vaults of the cosmos, where the remnants of stars whisper their final confessions, humanity's gaze pierces the veil through instruments of unparalleled ingenuity. These tools, forged from the collective ambition of astronomers across continents, unravel the enigma of crystallized white dwarfs, transforming distant flickers into profound revelations. Consider the pulsating heart of a dying star. Its rhythms captured not by a single eye, but by a symphony of telescopes spanning the globe, each contributing to a chorus that echoes the physics of solidification. As these stellar corpses cool, their interiors crystallize, a process once theorized in isolation, now illuminated by waves of data from space and ground alike. This chapter delves into the arsenal of observation and simulation, where each discovery refines our understanding of cosmic timelines, inviting reflection on the universe's measured descent into stillness. The revelation of Lucy, that emblematic white dwarf whose core gleams with the promise of diamond, emerged from a network of vigilance known as the Whole Earth Telescope. Conceived in the late 1980s, this collaborative endeavor unites observatories from disparate longitudes, from the arid plains of Texas to the high altitudes of Chile and beyond, ensuring unbroken scrutiny of celestial phenomena that unfold over days or weeks. 4 pulsating white dwarfs, whose surfaces throb with seismic waves akin to earthquakes rippling through stone, such continuity is essential. These pulsations, driven by gravity modes that probe the star's depths, reveal the transition from fluid plasma to crystalline lattice. In 1998 and 1999, then-Network turned its collective gaze upon BPM 37093, a white dwarf of exceptional mass, harboring nearly the Sun's heft within an Earth-sized sphere. Observations spanned multiple sites, amassing light curves that dissected the star's oscillations into precise periods. Asteroseismology, the art of interpreting these stellar quakes, disclosed an average period spacing suggestive of a crystallized core where carbon and oxygen ions had aligned into ordered structures, releasing latent heat that altered the cooling trajectory. This was no mere detection. It tested the boundaries of theory, confirming that in massive white dwarfs, crystallization commences earlier, under the crush of densities where matter behaves as a quantum fluid. The data painted a portrait of a star, partially solidified, its inner regions a vast crystal domain, while outer layers lingered in liquidity, a boundary marked by subtle shifts in pulsation modes. Such findings echoed earlier predictions from quantum mechanics, where the Coulomb potential between ions overcomes thermal chaos, imposing symmetry. Reflecting on this, one senses the universe's elegance. A dying star, in its senescence, achieves a form of crystalline perfection, its vibrations a final symphony conducted by the laws of physics. Building upon these targeted vigils, a broader canvas emerged with the advent of the Gaia mission, a sentinel orbiting beyond Earth's atmosphere, charting the heavens with astrometric precision. Launched in 2013 by the European Space Agency, Gaia has mapped the positions, distances and motions of over 1 billion stars, including a vast census of white dwarfs. By 2019, its data releases unveiled the first empirical confirmation of widespread crystallization, transforming speculation into certainty. Analyzing the luminosities and colors of thousands of white dwarfs within 300 light years, researchers identified a pileup in the cooling sequence, a clustering where stars lingered longer than expected, their decline stalled by the heat of solidification. This sequence, plotted as brightness against temperature, revealed a bifurcation, one branch for liquid interiors, another for those crystallizing, where oxygen-rich phases separated, driving convection and prolonging radiance. The mission's parallax, measurements accurate to microarcseconds, allowed precise distance estimates, refining masses and radii for millions of these remnants. In open clusters and the galactic disk, Gaia's catalog exposed variations tied to progenitor masses and metallicities, showing that crystallization manifests differently in carbon-dominant versus oxygen-heavy cores. For instance, in a sample of 15,000 nearby white dwarfs, the data confirmed that cores begin solidifying at temperatures around 10 million degrees, under pressures forging diamond-like lattices. This not only validated decades-old models, but extended them, suggesting that crystallization influences the age dating of stellar populations, pushing back estimates for the galaxy's oldest groups by billions of years. Philosophically, Gaia's revelations evoke a sense of cosmic archive. Each white dwarf, etched with the history of its birth cluster, contributes to a galactic chronology where the slow freeze of matter marks the passage of epochs. The mission's ongoing data, now encompassing proper motions that trace orbital histories, hints at dynamic interactions, mergers or ejections that further sculpt these crystalline fates. Peering deeper into the infrared veil, future horizons unfold. With the James Webb Space Telescope, a marvel launched in 2021, its segmented mirror unfolding like a golden lotus in the void. Positioned at the second Lagrange point, Webb captures the faint glow of cooling stellar remnants, where visible light fades but infrared persists, revealing secrets hidden from optical eyes. In recent observations of globular clusters like 47 Tucanae, Webb's near-infrared camera has mapped white dwarf cooling sequences with unprecedented depth, extending to the faintest members. These images, combined with archival Hubble data spanning decades, trace the evolution from hot progenitors to crystallized cores, refining models that incorporate collision-induced absorption, where hydrogen molecules in dense atmospheres dim the infrared flux. In 47 Tucanae, a cluster 16,000 light-years distant, Webb detected the truncation of the sequence where crystallization halts, further dimming, allowing precise age calibrations for these ancient stellar aggregations. Similarly, in Messier 4, the EE telescope resolved infrared excesses from debris disks orbiting polluted white dwarfs, disks of rocky remnants vaporized by their star's gravity, their spectra hinting at water-bearing minerals. Such findings speculate credibly on the recycling of planetary material, where crystallized stars accrete the detritus of shattered worlds, altering their cooling rates through episodic heating. Webb's sensitivity to mid-infrared wavelengths probes the photospheres directly, distinguishing between helium and hydrogen atmospheres, and identifying ultra-cool dwarfs on the cusp of black dwarf status. As missions progress, these observations promise to disentangle the effects of core composition on solidification, perhaps revealing exotic phases in magnetic white dwarfs where fields twist crystalline lattices. In this light, one contemplates the telescope's role as a temporal lens, compress engines into spectra, where the infrared hum of a white dwarf echoes the universe's inexorable chill. Complementing these orbital sentinels, vast mirrors on Earth's mountaintops endure the elements to track the subtle pulsations of white dwarfs, their apertures collecting photons across nights of unwavering focus. Facilities like the Very Large Telescope in Chile's Atacama Desert, with its quartet of 8-meter dishes, and the Keck Observatory atop Mauna Kea, harness adaptive optics to sharpen views distorted by atmosphere, resolving oscillations with periods from minutes to hours. These instruments monitor variable white dwarfs, such as those in the DBV class with helium atmospheres, where pulsations probe deeper layers unaffected by hydrogen opacity. Recent discoveries include ultramassive pulsators, like one observed with the New Technology Telescope. Its rapid throbs, faster than any known, indicating a dense, partially crystallized interior where gravity modes trap energy, revealing mass dichotomies. Ground-based spectroscopy dissects these signals, identifying mode line widths that differentiate rotational effects from crystallization boundaries. In surveys spanning years, observatories like the Large Synoptic Survey Telescope, now Vera C. Rubin Observatory, scan the skies nightly, massing time series data on thousands of white dwarfs, uncovering new variables in binary systems where tidal interactions excite additional modes. This ongoing vigilance extends asterosismology's reach, confirming that in clusters like Praecep, white dwarf pulsations align with crystallization models, their frequencies shifting as cores solidify. Speculatively, these observations hint at evolutionary pathways. Merged white dwarfs, born from binary coalescence, pulsate with anomalous energies, Their accelerated cooling recalibrated by latent heat release. Amid the hum of these giant eyes, a philosophical undercurrent emerges, the human endeavor to synchronize with cosmic rhythms, where each pulsation bridges the gulf between mortal inquiry and eternal processes. Yet, the extremes of white dwarf interiors elude direct gaze, compelling scientists to recreate them in silicon realms, supercomputer simulations that mimic the crush of stellar densities. At facilities like Argonne National Laboratory, vast arrays of processors model the molecular dynamics of carbon-oxygen plasmas, charting phase diagrams where liquids yield to solids under pressures of gigabars. These simulations, employing millions of virtual particles, reveal eutectic behaviors. In mixtures, oxygen crystallizes first, sinking to form denser cores while carbon floats, stirring convection that delays cooling by eons. Drawing from quantum Monte Carlo methods, they predict lattice structures, body-centered cubic for oxygen, diamond for carbon, stable at temperatures rivaling stellar hearts. Recent advances incorporate magnetic fields, simulating dynamos in crystallized layers, where rotation induces currents, potentially explaining observed magnetism in some white dwarfs. In ultramassive cases, simulations explore sedimentation, where heavy elements gravitate inward, altering neutrino emission and further refining cooling curves. These digital analogs, validated against asteroseismic data, extend to speculative frontiers. How crystallization in binary mergers accelerates, forging hybrid cores that challenge standard evolution. Reflectively, these computations mirror the universe's own computations, algorithms of physics unfolding in code, bridging the infinitesimal and the immense, where human ingenuity recreates the stellar forge in pursuit of truth. Culminating these efforts, astronomers recalibrate the chronometers of white dwarf cooling, weaving crystallization into narratives of galactic antiquity. Traditional models assuming uniform cooling underestimated ages by overlooking phase transitions. Now incorporating latent heat release, they extend timelines. In the solar neighborhood, Gaia's white dwarf luminosity function, a histogram of brightnesses, reveals a downturn at faint ends. Interpreted as the galaxy's age limit, around 13 billion years, adjusted upward by merger contributions, where binaries fuse into single, hotter remnants that cool anomalously. For clusters like the Hyades, white dwarf sequences yield ages aligning with main sequence turnoffs. But crystallization refines this, accounting for metallicity dependencies where metal-poor stars solidify sooner. Population synthesis codes, fed with these updated physics, reconstruct star formation histories. Bursts in the thin disk, steady in the thick, each imprinted on white dwarf distributions. Speculatively, this recalibration probes dark matter's influence, where halo white dwarfs, if crystallized, could trace primordial populations. In this recalibration lies a profound mystery, the universe's autobiography, inscribed in fading lights, where each adjusted age whispers of origins veiled in time's expanse. Through these instruments and inquiries, the crystallized white dwarf emerges not as an endpoint, but as a beacon illuminating cosmic evolution. The tools of science, from global networks to digital simulations, converge on this mystery, each layer of data deepening our communion with the star's silent legacy. In their collective light, one discerns the universe's philosophical core, a realm where matter's transformations mirror the soul's quest for order amid entropy's tide. In the quiet expanse of the cosmos, where stars burn as fleeting candles against an infinite night, the diamond stands as a symbol of eternity. To humanity, these crystalline treasures forged in the crucible of Earth's depths embody permanence, tokens of love, emblems of wealth, fragments of time captured in unbreakable clarity. They are rare, wrested from the planet's hidden forges, each gem a story of pressure and transformation. Yet in the grand theater of the universe, diamonds are not mere jewels but tombstones, the final legacy of stars that have exhausted their fiery youth. The white dwarf Lucy, its core a diamond lattice spanning thousands of kilometers, is but one among billions in the Milky Way, each a silent monument to a star's life and death. These celestial relics, invisible to the naked eye, gleam faintly in the interstellar void, their crystalline hearts enduring through epochs that dwarf human history. In their silent radiance they whisper a profound truth. The universe, in its relentless cycles, crafts not only chaos but an elegance that outlasts time itself. This revelation of diamond stars, born from the cooling cores of white dwarfs, invites a meditation on permanence in a cosmos defined by flux. Civilizations rise on fragile worlds, their cities gleaming briefly before crumbling into dust. Empires fade, their stories etched in stone or memory, yet all succumb to the erosions of time. Planets orbit, their surfaces reshaped by wind, water, or fire, their histories transient in the galactic ledger. Even the stars, those titanic furnaces that birth the elements of life, flare brilliantly only to dim or explode, their light a temporary defiance of the dark. But the diamond cores of white dwarfs endure, their atomic lattices locked in a stability that could persist for trillions of years, timescales so vast they stretch beyond the universe's current age. These relics, formed as stars shed their outer layers and collapse into dense embers, are supported by the quantum resistance of electrons, a force that defies gravity's crush. As they cool, their carbon-rich interiors crystallize, releasing latent heat that sustains a faint glow, a whisper of warmth against the cosmic cold. In this endurance they stand as sentinels, outlasting galaxies, their crystalline forms a testament to a universe that preserves as fiercely as it destroys. The beauty of these diamond stars lies not in their radiance, for their light is faint, a mere echo of their former glory. Rather, it resides in their transformation, a poetic alchemy where fire yields to crystal, chaos to order. Stars in their youth are furnaces of creation, forging hydrogen into helium, then heavier elements, seeding the cosmos with the building blocks of planets and life. Their deaths, for those of modest mass, are not cataclysms but gentle exhalations, shedding luminous clouds to reveal white dwarf cores. Within these remnants, under pressures where matter is compressed to unimaginable density, carbon atoms align into lattices akin to terrestrial diamonds, yet on a scale that humbles earthly geology. This process, confirmed through the pulsations of stars like Lucy and countless others, is a universal fate for white dwarfs, as evidenced by astroseismological studies and data from space observatories. The universe, often cast as a realm of destruction, where supernovae shatter and black holes consume, reveals here a capacity for elegance, crafting monuments of astonishing precision from the embers of its stars. Each diamond core is a masterpiece, its facets unseen, its beauty a secret held by the cosmos, enduring in silence as galaxies whirl and fade. This cosmic abundance challenges human notions of value, turning the mirror inward on what is deemed precious. On Earth, diamonds are rare, their scarcity fueling desire, their clarity symbolizing bonds unbroken. A single gem, no larger than a grape, can command fortunes, its worth rooted in its geological rarity. Yet in the Milky Way, diamond stars number in the billions, their crystalline cores dwarfing all terrestrial treasures combined. Lucy alone, with its core estimated at 10 billion trillion carats, underscores this disparity, a single white dwarf harboring more diamond than could ever be mined from Earth's crust. Studies of white dwarf populations, drawn from surveys like those by space telescopes, suggest that crystallization is a common endpoint, with many, if not most, white dwarfs forming such structures as they cool. The carbon and oxygen in their cores, forged in the fusion of their progenitor stars, align under pressures billions of times greater than those in Earth's mantle, creating lattices that span planetary dimensions. What humanity cherishes as unique, the universe produces with casual extravagance, scattering diamonds across the galaxy as naturally as it scatters stardust. This paradox of value extends beyond diamonds to the very elements that compose life. Carbon, oxygen, nitrogen. These are not Earth's alone, but the universe's currency, forged in stellar cores and dispersed through cosmic winds. Gold, revered through human history, is born in the violent deaths of massive stars, its atoms scattered in supernova explosions. The realization that what is prized as rare is abundant in the cosmos invites a humbling reflection. Value is a human construct, a lens through which we view a universe indifferent to our measures of worth. The diamond stars, in their silent abundance, suggest that rarity is not intrinsic but contextual, a fleeting human perception against the backdrop of cosmic profusion. Yet rather than diminishing these treasures, this perspective elevates them, revealing the interconnectedness of all matter. Earth's gems and life's elements as echoes of stellar legacies, woven into the same tapestry that holds the galaxy's crystalline relics. The destiny of our own sun casts this reflection into sharper focus, a poignant thread in the cosmic narrative. In some 5 billion years, the sun will exhaust its hydrogen, swelling into a red giant that engulfs the inner planets. Mercury and Venus will vanish, consumed by its fiery embrace, while Earth may linger, scorched but intact on the edge of annihilation. The sun will shed its outer layers, casting a luminous nebula into the void, leaving behind a white dwarf no larger than Earth, yet nearly as massive as its progenitor. Supported by electron degeneracy pressure, this remnant will cool over billions of years, its surface dimming from searing white to a dull glow. In trillions of years, timescales that render the universe's current age a mere prelude, its carbon-rich core will crystallize, forming a diamond lattice that spans its interior. This cosmic jewel, the sun's final monument, will drift through the galaxy, a silent testament to the star that once nurtured life, its crystalline heart enduring as Earth's own story fades into cosmic obscurity. The inevitability of this transformation evokes a bittersweet awe. The sun, the anchor of our world, the source of light that has painted landscapes and sparked life, will one day join the ranks of the galaxy's diamond stars. Its legacy will not be erased but transformed, its essence preserved in a form that defies the erosions of time. This destiny, grounded in the same physics observed in Lucy and other white dwarfs, underscores the universe's capacity for renewal, where endings are not final, but preludes to new states of being. The carbon in the sun's future core, once part of the fusion that warmed Earth, will become a diamond linking our star to the billions of others that share this fate. It is a reminder that the universe recycles its matter, weaving the atoms of stars into planets' life and ultimately crystalline relics that endure beyond imagination. The closing scene unfolds in the mind's eye, a galactic vista strewn with hidden diamonds. The Milky Way, a spiral of light and shadow, harbors these silent relics, their faint glow blending with the vibrant fires of living stars. Each white dwarf, a former sun, now carries a crystalline heart, its lattice a record of its fiery past. These jewels, invisible to all but the most sensitive instruments, are scattered across the galaxy, waiting in the cold silence of the void. They are not mere curiosities, but archives of cosmic history, their atomic bonds preserving the chemical signatures of their progenitor stars. As galaxies merge and stars fade, these diamond cores may endure, their stability a defiance of entropy's advance. In the far future, As the universe expands into a vast, darkened expanse, they could become the last luminous objects, their glow sustained by the lingering heat of crystallization, a final chorus of light in a silent cosmos. This vision, speculative yet rooted in the physics of white dwarfs, invites a final reflection on transformation. The universe, often cast as a realm of impermanence, reveals through these diamond stars a capacity for enduring beauty. Destruction gives way to creation, chaos to order. As stars become monuments that outlast their own light, the pulsations of white dwarfs measured through asteroseismology confirm this process, their vibrations revealing crystalline cores in countless remnants. Surveys of the galaxy, conducted by observatories and space missions, estimate billions of such relics, their abundance a testament to the universality of this fate. The latent heat of crystallization, delaying their cooling, adds a temporal dimension, as if the universe itself pauses to savor these transformations. In the end, the diamond stars stand as a profound reminder. Even in death, stars are not extinguished but transformed. Their crystalline hearts, gleaming in the cosmic night, embody a permanence that transcends human understanding, a beauty that persists in silence. They challenge perceptions of endings, suggesting that the universe's narrative is one of continual renewal, where fire becomes crystal and transience yields to eternity. As humanity gazes upon the night sky, those faint points of light, some burning, some crystallized, carry a message of hope and humility. In the vastness of the cosmos, transformation is the truest constant, and even in the quiet of death, the universe crafts monuments that shine forever. The story of a diamond star is not only a story about physics, nor only about astronomy. It is a story about permanence in a universe defined by impermanence. The weight of permanence in a universe of change, the cosmos is a place of relentless transformation. Stars ignite and exhaust themselves. Galaxies collide and unravel. Planets rise, burn, freeze, and vanish. Even black holes, those seemingly eternal anchors of gravity, are destined to evaporate across unimaginable spans of time. Everything changes, everything decays, and yet in the quiet aftermath of stellar death there remains something different. A crystallized heart of carbon and oxygen, hardened against entropy, luminous in its silence, a diamond star. It does not blaze with fire. It does not roar with fusion. It does not collapse into oblivion. It endures. Here lies the paradox. The universe that erases all things also leaves behind monuments, tokens of eternity, cold, vast diamonds the size of worlds, humanity's fragile symbols. On Earth, diamonds are a rarity. We treasure them as symbols of permanence, of unchanging love, of wealth and memory. We cut them into shapes that capture light, wear them close to the skin, pass them from generation to generation as tokens against time. But when we set our gaze upward, when telescopes like Gaia and Webb reveal the sky's hidden architecture, we discover that the universe cares nothing for rarity. It produces diamonds not in carats, not in handfuls, but in masses that outshine planets. Our greatest treasures are to the cosmos incidental. This discovery destabilizes us. It humbles our values. It asks, what is truly rare in the universe? Not diamonds, but life. Not carbon lattices frozen in silence, but consciousness that can look at them, name them, wonder at them. A future written in crystals, the fate of Lucy, the diamond star in Centaurus, is not unique. Our own sun, when its hydrogen is exhausted, will swell into a red giant, shedding its outer layers into a glowing nebula. What remains will shrink into a white dwarf, a dense, cooling ember no larger than Earth, yet heavier than 1,000,000 Earths. And as aeons unfold, its heart will freeze, crystallize, and harden into a monument of diamond. In that future, Earth itself will already be gone, its surface boiled, its crust erased, its orbit perhaps disrupted. But the sun's diamond heart will remain, drifting in silence long after memory and history vanish. The last record of our existence may not be written in books or monuments, but in the quiet crystallization of a star we once called home. Cosmic chronologies rewritten. The discovery of crystallizing stars did more than astonish. It rewrote the timelines of astronomy. For decades, scientists used white dwarfs as clocks, measuring the cooling rate of these stellar corpses to estimate the age of stellar populations. But diamonds resist cooling. They trap heat in their crystalline cores, slowing time's passage. The clocks of the cosmos are not as simple as once believed. Every diamond star is not only a monument of permanence, but also a distortion of chronology, a reminder that even time itself bends around matter's secret architecture. A universe of hidden monuments. If Lucy is one, then there are countless more. The Milky Way alone holds billions of white dwarfs. Over cosmic time, each one will crystallize. The galaxy will become a graveyard of diamonds, drifting through spiral arms, unlit, unseen. Across the universe, in every cluster, every ancient stellar population, these silent monuments accumulate. We live not in a universe of fire, but in a universe that with time fills with diamonds. The thought unsettles. It redefines beauty. It reframes value. It teaches us that the universe does not treasure what we treasure. It treasures endurance, the mirror of fragility. In the presence of such permanence, our own lives appear impossibly fragile. We live decades, perhaps a century. Civilizations rise for thousands of years, then fall into memory. Even species endure for only millions before yielding to extinction. Compared to a diamond star, crystallizing across billions of years, our existence is the flicker of a match in the wind. And yet there is a difference. The diamond star endures without awareness. It is permanence without perception. We, by contrast, are fragile, but we perceive, we wonder, we give meaning. It may be that in the hierarchy of the universe, permanence is not the highest value. Perhaps awareness is. Perhaps consciousness itself is the rarest diamond. Beyond value, toward wonder, what then is the lesson of Lucy? That value is relative. That rarity is perspective. That beauty can take forms we never imagined. It reminds us that the universe is not a human story. It is larger, stranger, more extravagant than our categories. Yet it also whispers something comforting, that transformation is not only destruction, that the end of fire is not silence but crystallization, that death itself in the cosmos can be beautiful. Closing reflection. In the silence of interstellar space, Lucy drifts. It does not shine as it once did. It no longer burns. Yet it endures, an eternal diamond, a star transfigured into jewel. There are no eyes to see it there, no beings to touch its surface. It will remain, regardless of witness, a monument to the laws of physics, to the transformations written into matter itself. And still, here on Earth, fragile beings of flesh and thought imagine it. We name it, we tell its story. We place it in the gallery of human wonder. Perhaps this is the true diamond. Not the star itself, but our ability to recognize it, to see permanence in the impermanent, to find beauty in death, to lift our eyes to the night sky and know the universe is filled with hidden jewels. And one day the sun that gave us life will join them, when everything we know has vanished. When Earth is gone and memory erased, a single crystal heart will remain our final monument, shining in silence, a jewel of eternity.